Hey guys, I want to go ahead and talk about some of these derivatives of exponentials. But before I do that, I want to go ahead and do some of these indeterminates. If you notice the limit as x approaches 0 um, of this expression right here, we want to go ahead and evaluate it. The only problem is it's 0 times cosecant, that's a reciprocal identity of sine. Well, that's going to give you 0. 0 times 0 is indeterminate, but what we want to do is use L'Hopital rule in order to rewrite this. The only problem is I have to have a fraction. So what I'm going to do is I'm going to rewrite this guy as x squared divided by sine squared of x, because I know that cosecant is the reciprocal identity of sine. So now I have 0 over 0. Well, I can go ahead and take the derivative, and that gives me 2x. Well, this guy, remember, sine squared of x is the same thing as sine of x to the second power. Some students get confused. So bring this guy down. That gives you 2 sine of x times the derivative of the inside, which is cosine of x. Now I can go ahead and plug in my 0. 2 times 0, well, unfortunately that's 0 again. And then sine of 0, well, that's 0 again. I can go ahead and simplify this guy here. And I'm going to end up with the limit as x approaches 0 of x divided by sine of x times cosine of x. Well, I still get 0 over 0, so I have to go ahead and do it again. Well, L'Hopital rule again, the derivative of x is 1. Over here, I'm going to sine times cosine that. Well, that's a product rule first. Times the derivative of the second. The derivative of cosine is negative sine. Plus the second times the derivative of the first. The derivative of sine is cosine. Okay. And it looks like I'm going to run out of room. But for this one, you should get 1 over cosine squared minus sine squared of x. Well, if I take x approaches 0, well, sine of 0 is 0, and this guy is cosine of 0. Cosine of 0 is 1, so you're going to get 1 divided by 1, which is 1. Okay? Hopefully that makes sense. Sorry, I ran out of room. Over here, we get the same thing. We have to go ahead and rewrite cotangent. So I'm going to have 1 over sine of x minus cotangent is cosine over sine. So now that we have that, we can go ahead and put this together as 1. So we have the limit as x approaches 0 of this guy. So let me go ahead and make some room here. So I'm going to have the limit as x approaches 0 of 1 minus cosine of x divided by sine of x. Now that that's simplified, I can go ahead and plug in my 0. Cosine of 0 is 1. 1 minus 1, I get 0 over 0, indeterminate. So I can go ahead and take the derivative. The derivative of 1, well, that's 0. The derivative of cosine, well, that's negative sine. So this is negative sine, but because of the other negative, it makes it positive sine. So I'm going to have positive sine of x. The derivative of sine is cosine. Well, what's the limit as x approaches 0 of sine over cosine? Well, sine of 0 is 0. Cosine of 0 is 1. And the answer is 0. Alright. Sorry guys, I ran out of room, but if you can see that all you have to do is rewrite it, simplify it, and you can go ahead and actually do these. When we go into taking the derivatives of exponentials, you probably already learned the derivative of an exponential. Let's say we have a to the power of x. Well, the derivative is just the same thing, a to the x, the exact same thing, but then you have to multiply it by ln of a. Okay, so for this guy over here, the first one, we have f prime of x. F of x equals this part. So the derivative starts off with the original problem. So a to the x. So you have this guy right here. So we're going to have 3 to the power of 5x cubed. But now we got to take the derivative, or I'm sorry, we got to multiply by log, the natural log of this a value. Well, what's the a value? Well, it's 3. Okay, or the base value. But now notice we have something inside. There's a function inside of this function, so we have to use a chain rule. So this becomes 15 or times 15x squared. Okay, and I would go ahead and just leave it like that. You can go ahead and put the 15x squared in the front. Now be careful, do not multiply 15 times 3 and think it's 45. That's incorrect. Okay, if you want, you can put 15x squared. If you want, you can put 15x squared ln of 3, and then times 3 5x cubed. Okay, you can go ahead and do that, but do not multiply 15 times 3, because this is the base of this exponent here. Okay, sometimes students get in the habit of doing that, and that's incorrect. Let's go ahead and do the next one. 3 to the x squared power. We have f prime of x. Well, it tells us that we're going to go ahead and do the same thing when we take the derivative, write the same one out. And now we got to take the natural log of the base. The base is 3. But since we have something inside, we have an x squared, we got to take the derivative of that and we multiply by 2x. And that would go ahead and be your derivative. Now again, be careful. Do not multiply 2 times 3 and think it's going to be 6x to the x squared power. That's incorrect. Okay, you can go ahead and just leave it like this, separated. And that's perfectly fine. Another way of thinking about it is, let's say you have 3 squared times 2. Okay, well, if I do the math in that, well, 3 squared is 9. 9 times 2, well, that gives me 18. Okay, if I multiply 2 times 3, well, that's going to give me 6 to the second power, 6 squared, and that's actually 36. These are not the same values. Okay, that's why we don't go ahead and multiply the 2 and the 3. The base goes along with the exponent. Okay, let's go ahead and do another one here. Now this one here, if you remember, ln of x, the natural log of x, well, the derivative of ln of x is 1 over x. The problem is this guy is not ln of x, it's log base 3. Now I haven't seen any of these on the AP exam. I guess you might see one of these, but what I'm going to do is I'm going to go ahead and rewrite this using the change of base formula. And remember, the change of base says I can change the base. I can change the base using the log to a different log. So I'm going to use ln, and all I'm going to do is take ln of the top, okay, divided by ln of this guy here, ln of 3. Okay, and that's what I have. That's the same thing as saying ln of 4x squared times 1 over ln of 3. Okay, now remember, this guy is just a constant. So when we're taking the derivative, this guy's just more like a multiplier. All right, so you can cover this up if you'd like. So what's ln of 4x squared? Well, anytime I take the ln, you do 1 over whatever this guy is. So it's 1 over 4x squared. But remember, you already have the ln on the bottom. So if you want to put the ln to the ln of 3, okay, times, we have something on the inside, a function on the inside, 4x squared. So the derivative of 4x squared is 8x. So this ends up becoming 8x divided by 4x squared times ln of 3. Okay. Next we'll do one more. Okay. We have log base 5 of 4x to the 6. Let's go ahead and rewrite that. So that's going to give us ln of 4x to the 6 divided by ln of 5. And this is the old change of base formula. Okay. I'll go ahead and do it down here. Now remember, ln of 5, that's just a constant. I'm going to go ahead and rewrite this 1 over ln of 5. Okay. The derivative of ln, well, it's 1 over 1 over 4x to the 6th. Okay, and that's all I'm doing. Whatever it is you're taking the natural log of, just 1 over that value. Okay, the 1 over ln to the 5th, ln of 5, I'm sorry, is just, that's just a multiplier. You can just go ahead and cover it up. Times ln of 5, okay? Okay, that's just your multiplier. Think about it this way. For example, I tell my students, well, what's the derivative of 3 sine of x? Well, just cover up the 3. What's the derivative of sine? Cosine. And the 3 is just a multiplier, so it's 3 cosine of x. Okay, same difference here. Okay, so 1 over 4x to the 6th times 1 times the ln of 5. But now take the derivative of the inside, so that's going to give you 24x to the power of 5. Okay, so those are a few examples of taking derivatives of exponentials. We also did indeterminate forms. Let me know if this is helpful, if you need me to do any others. Alright guys, good luck. I'll see you guys next time.